A warm welcome to the fifth film in our Floors and Ceilings series, in which we examine the characteristics of beam-type floors and ceilings. Beam-type floors and ceilings consist of load-bearing members over which a series of panels are laid. Where span widths are particularly long, it may be necessary to use several, up to 3 layers of load-bearing members in a lattice formation upon which the flat floor sheeting is then laid. Floor systems of this type comprise primary members to span the opening, followed by secondary and possible tertiary members. The depth of the final floor structure depends on the way the members are arranged. If the layers of members are laid one on top of another, the total depth of the entire load-bearing system is equal to the sum of the depths of all the layers. Constructing this type of floor is relatively easy because one member beam can simply be laid on top of another. It also takes advantage of the multiple span effect already mentioned. However, the large total depth of the load-bearing framework can be problematic. The opposite is true if the members lie one inside the other, that is to say, that one member is fixed to the next so that the top edges of all the members sit at the same height rather than one on top of another. This type of construction is more complex because each member must be held in position temporarily until it is finally fixed in place because bearing points are subject to shear force. There is no structurally advantageous multiple span effect, but the total depth of the load-bearing system is significantly smaller, the depth of the primary member in fact. Now let us take a look at the materials used. As for a solid reinforced concrete slab, here too reinforcing steel absorbs the tension forces that occur at the bottom of the members of a non-cantilevered slab. These members are known as beams or T-beams and the resulting floor as beam-type or T-beam floor. Their small construction depth is due to the fact that the pressure zones of both beams and slab lie in the same place. The construction is no deeper than the beams it contains. Because the reinforcing steel in the beams and slabs runs in 2 directions, the slab benefits from the multiple span effect. Here you can see the corrugated steel floor again. This beam-type construction is made up of steel I-beams and corrugated steel decking sheet. Both beams and decking sheets are subject to bending stress, which means that compression and tension forces are at work on the upper edges of both components. In the case of the steel I-beams, the forces are absorbed by the upper and lower flanges of the beam, which are joined by the vertical web. The load-bearing capacity of the sheeting that is bolted onto the beams is a result of the corrugated profile, which means that both compression and tension forces are transferred to the horizontal surfaces of the crowns and troughs. This is what a timber joist floor looks like. The timber joists are placed close together because the boards or wood composite sheeting laid over them can only be used for short span widths. While concrete and steel beams have a width-to-height ratio of 1:1 and may even be wider than they are deep, timber joists always have a rectangular cross-section and are laid on their shorter side. As a result, and unlike reinforced concrete and steel beams, the section of timber joist is not structurally optimized. Now let us take a closer look at a timber joist floor. You already know how to estimate the dimensions of a wooden beam. The height should be approximately 1/20th of the span width and the width between half and a third of the height. For a span width of 4 meters, this gives a height of 20 centimeters and a width of between 7 and 10 centimeters. For a span width of 7 meters, the height would be 35 centimeters and the width 12 to 18 centimeters. As the maximum timber size that can be cut from a tree is 28 centimeters, beams for this span width would have to be made from glued laminated or engineered timber. Glued laminated timber is produced industrially by gluing together in layers solid timber cut from trees. The bonding together of these layers creates an engineered product that exhibits the properties of solid wood at much greater dimensions. In the first house that my brother and I built in 1994, the floors were made of glued laminated timber due to the large span widths. This photograph illustrates another fundamental principle of the timber joist floor. The beams are always placed between 60 and 90 centimeters apart from center to center. The first joist is placed a short distance from the rising wall to compensate for tolerances and to allow the wall to be finished. The distance between two of these parallel edge joists should be divided equally to give a reasonable centre-to-centre spacing for the remaining joists. The boards or wood composite sheeting laid on the beams then project slightly to fit flush with the wall. This photograph taken in Felix Haustein's house shows how the edge joists are placed in relation to the rising walls. The photograph and the accompanying drawings also explain how a wooden beam is supported on a wall. The joist is fixed to a concrete ring beam. Flashing tape is used to prevent damp ingress into the timber. Specially cut bricks are then used to bring the joist into line with the octametric system. Hopefully you will remember that a floor is able to transfer horizontal loads if it acts as a rigid plate. If timber joist ceilings are to have this property, the decking laid over the beams must exhibit this plate effect. This happens when the individual boards are connected together or continuous flat steel strips bands are placed diagonally on top of them. This plate effect can also be achieved more simply by the use of large format wood composite sheets, though this will alter the appearance of the ceiling below. Summary: beam-type floors and ceilings consist of load-bearing members over which a series of panels are laid. With long span widths, it may be necessary to use up to 3 layers of load-bearing members. Primary members span the opening, followed by secondary and tertiary members. The depth of the final floor structure depends on the arrangement of the members. If they are placed one on top of another, the total depth of the entire load-bearing system is equal to the sum of the depths of all the layers. The total depth of the load-bearing system is significantly smaller if the members lie one inside another, so that the top edges of all the members sit at the same height. Beam-type floors can be made of reinforced concrete, steel, or timber. Why not take a look at the 6th and final film in our Floors and Ceilings series, which explains how stairs are built into floors.